Okay, hello everyone. Yeah, how is everyone doing?
Hello, sir. Good evening, sir.
Good
Good
evening, sir.
evening. Good evening. Yeah, we'll just wait for a couple of minutes. People are just joining in. Yeah.
Sure, sir.
Okay, everyone. So welcome to this live session. So in this live session, we will it's an open session for week 11. So if you have any doubts regarding week 11, you can ask, right? So in general, uh, have you gone through the lectures? What are your initial thoughts on week 11? Uh, do you see something different? Yeah, anything on the chat?
Sir, for now, I haven't gone through week 11. I had some doubt in previous term quiz papers. Could you please solve that? Make me clear my doubts.
Yeah. So actually, the next two sessions we'll be focusing on, the quiz preparation. So
There are no two sessions. I think tomorrow only there is one session of revision.
on Saturday also, I believe it's there.
No,
Okay.
sir. It is not there. It has been updated that there is no session on Saturday.
Okay. Sure. So let's yeah, I'll give priority to week 11, and once if there aren't any doubts for week 11, then we can definitely go through
So
the
these are a couple of questions only.
yeah, okay. Yeah, so let me just see if others have any doubts in week
Okay, sir.
11. Yeah,
Sure.
then we'll get it. Yeah. All right, any specific doubts on week 11? Any topic which you found difficult? No response. Okay, then maybe let's try solving some of the questions in the quiz. Yeah. Uh, Sorry, I couldn't get your name.
Yes,
Aditi?
sir. Yes, sir. Yes, sir.
Okay, Viraj is telling something about reductions. Viraj, anything specific or in general? How useful are reductions? Okay, all right. ठीक है. Okay, so okay, what about others? Do you want to look at the quiz questions or do you want to look at week 11? Which should we prioritize first? You can reply on the chat.
Quiz question, sir.
Okay. Okay, Aditi. Yeah. Which question did you have a doubt?
Sir, it is set number D, question number 14.
Just
Which quiz, Aditi?
yeah. Which quiz are you?
Quiz 2, set number D.
Last time. Okay.
Last previous term question paper. It is. Should I share the link?
Yeah, you can share the link. Yeah.
Okay, sir, fine.
Is it there on Discourse?
No, sir. Previous year in diploma, yes, it may be in discourse, but in diploma we got that question papers. Yes, sir. Sent the link.
All right. Okay. Okay, which question?
Question number 14.
Okay, let's see that. Uh, One minute.
Sir, it is about max heap and list is given. Sorry, array is given and we have to insert value repeatedly in an empty heap. That question.
Yeah, 1 minute. I'm just trying to log in. I think it requires an online degree. Log in. Okay, got it.
Okay, sir.
Okay. Question number?
14.
Okay. Okay, so let's read the question, right? So consider the max heap, this thing built by repeatedly inserting values into an empty heap. Which of the following could have been the last element inserted into this heap? Okay. Yeah, so what is your doubt?
Sir, why only 38 is the answer? Why 75? Sorry, 75 and 50 cannot be also inserted in the last. In the last, only 17 and 30 can be inserted according to my understanding.
Okay. So let's try to see what this is, right? So this is, we can just quiz this. Yeah. Consider a max heap, which is this, right? Yeah, built by repeatedly inserting values into an empty heap. Which of the following could not have been the last element? Okay. So let's try building the heap, right? So remember it's a max heap, right? So what is the property of a max heap? Yeah. What are the properties do we know? Aditi or someone else?
Yes, sir. So it will start from 95.
No, in general, what are the properties of a max heap?
Total, there are three nodes. The left one, the middle one is like the middle node, and the left one is lesser than the middle one, and the right one is the greater than the middle one.
No,
The root element.
it is not the property of heap, I guess. I mean, the heap properties are that they are following certain order, either max heap or min heap, being the parent node should be smaller than the left child and the right child.
Yeah, that is the only property.
And
Okay.
it should be filled in the
Parent
order of left to right.
parent node should be
Greater than.
Greater than equal to its child node.
right, and here min heap.
Parent node should be less than equals to children.
All right, and binary tree.
Left child should be less than parent node, and right child should be greater than parent node.
Left child should be less than parent. Okay, right child should be greater than parent. All right. Okay, so this is a max heap, right? So the root node should be the largest, right? Okay. Okay. So let's try.
Sir, can I ask some question to Aditi before you proceed?
Yeah. Go ahead.
Aditi, like, what is your logic behind saying that 30 and 17 can be the last inserted element?
As we arrange the this array into a maxi form, so yes, at last only 17 and 30 are coming. So by
But
that,
we are not heapifying this list. We are inserting one element one by one.
sorry, it is heapified. Then only 17 and 30 are in.
I guess you are applying that property that we have to only heapify the parent elements. We don't need to heapify leaf elements. Then in that way, we can heapify the complete list.
Here it is ordered. No, it is not necessary that in all the cases we get the ordered heap. We have to sometimes maintain the heapify property.
Yeah, like if we have to create the heap, then we have to definitely maintain the heapify property. And what do you mean by like ordered heap?
Sorry, what did you say?
Like you said something about ordered heap. So what do you mean by ordered heap?
I mean to say that here it is given an order that if we create a heap, it is already in max heap. Okay.
You are saying this list is already in max heap.
Yes.
It is telling us to consider the max heap. So yeah, it is even already in a max
In
heap.
case we would insert 96 after the 30, then we have to heapify in order to maintain the max heap property.
Yeah, after inserting, we have to heapify, right?
So we are creating the heap by inserting only, no?
Mm-hmm.
Okay. So let's start. Let's look at the problem. So they're saying this has to be a max heap, and it is built by repeatedly inserting values into an empty heap, right? Okay. So what does that mean? So first I insert 95, and since that's the first, I don't have to do anything, right?
Sir, the question asked not about building the max heap. It already given as max heap. We have to specify the question as which of the following could not have been the last element inserted into this heap. So we actually need the
No, Pras,
options to check.
we have to create the heap. Here, in the question is that we have to insert the values into an empty heap.
No, it says it is built by repeatedly inserting values. So it is already consider the max heap. It is written consider the max heap.
Yes, right.
Okay, so let's see now. So that's what I'm saying. If I take this as 95, this is 75, this is 84, right? So this is 50, this is 38. This is 64. This is 18. Is it till now? Is it satisfying this Max Heap property?
Yes, sir.
Okay. 64, 80, then 17, and then
30.
30. Okay.
Yes.
Okay. So yeah, as Prash was saying, somehow this is the Max Heap which we have got, right? And it is not necessary that we first encountered 95, then we encountered 75, then we encountered 84, then we encountered 50, and so on, right? That's not the case. Okay, these elements could have come in any order to us while we were building the heap, right? But after we do all of this, this is the final heap which we get. Is that clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now the question is, which of the following could not have been the last element inserted into this heap? Okay. So let's look at the options. 75, 50, 38, 30. 75, 50, 38, and 30. Okay. So yeah. So how will we tackle this problem? What do you think? What do you think should be done? So they are saying which of the following could not have been the last element inserted into the heap. So one step before this, we have to assume that like whichever is the option, that should not be there, right?
Yes, sir.
Or is there some other way we can do it?
Sir, I think this is the option that we have to manually check for each option and try to insert the element in the last position. If we are getting the same heap, then that option is correct, otherwise it is wrong.
Can we eliminate some of them from this? Which
Viraj,
option
can
can?
you elaborate? Sorry, sir. Viraj, can you elaborate the procedure you told about?
What I am saying is like for 75, if we have to check, then what we will do is like we'll insert 75 at last in the last. Like
No,
whenever we are trying.
no, but before that, what will the heap look like? Till then, it also should be a max heap, right?
Yes.
So, sir, that's what I'm saying. Na, we will start building heap by inserting one by one element. Like start with one element, then proceed.
Okay. Any other solution? So Snail is asking, do we need to check with 75 and 50 since they are parent nodes?
That's only the doubt, Snehil, because they are telling we cannot insert the last element. And answer is telling only 38 cannot be inserted at the last. We can insert 75, 50, and 30. So why we can insert 75 and 50?
From answer, what I concluded about was that 38 is the midpoint. So probably the midpoint cannot be inserted at the last, whether it being min heap or max heap. But that was concluded based upon the answer.
Okay, so okay, let's try something. Okay, let's try for one of the options. So yeah, so let's say if it was 75, like how do we check for 75? One thing is we just remove 75 from here, right? And if we keep that as 84, 80, and if we keep this as 50, this can be This can be,
Sir, if we delete one element in heap, so we insert, and if we delete a element in heap, then okay. So you are not inserting 75 right now. You are only deleting 75.
no, I'm not deleting 75. I am just thinking of the heap which would have been constructed before. Let's assume 75 was the last element. Okay.
Okay. Yes.
So in that case,
Sir, same thing I was trying to say like earlier.
okay. Yeah, go on.
Like I was saying that like we will consider a heap that we have built up. Like only the last element is remaining. Like here in this case, 75 is remaining. So if you want to see like what will be the leaf before inserting this element, so we will simply delete 75 from this heap, and then again try to insert 75. If we get the same heap, then 75 we can insert in the last position, and we will get the same heap.
Okay.
And similarly, we can check the same procedure with all the 4 options.
Yeah. So one thing from this is, yeah. So for example, 30, right? If you delete 30 and if you insert 30 again, right?
Hmm.
You are bound to get the same heap.
Yes.
Do all of you agree with that?
Yes, sir.
Right. So clearly 30 is ruled out. Okay.
And sir, snail is like telling a good point. I think this should also be considered.
Yeah. So since 75 and 50 are parent node, it is possible that they can be inserted as last elements and then they got heapified. Okay. Yeah, Snail, can you elaborate? What do you mean by that?
Sir, I think
So
he's okay.
what I'm trying to say is, even if we insert 75 as the last or 50 as the last element, there is a good possibility that after heapification, we'll get something like the same heap, where 75 and 50 are both parents having children nodes that are smaller than them. So we can
Okay.
rule them out too. And the only option then what we've left with is 38. Since it does not have any children, we can assume safely that it was not inserted last, because if it was inserted last, it will have to get heapified at some place, and it will have at least one child node.
Yeah, by heapification, it will regain its position again.
But is that always the case?
Yeah, that is the question, sir.
Not necessarily,
So,
sir, but by theory of elimination for this question, we can eliminate 75 and 50 using this.
okay. So let's check this. So everyone, are you clear that why we can't keep like why 30 is eliminated? Because it's clear, right? If I delete 30 and if I insert 30 again, I'll definitely get this. I cannot get any other heap.
Yes, sir. That's clear.
All right. Okay. So now we are left with these 3, right? Now, yeah, one way to check this is like what Viraj was saying, delete it and insert it again and check whether you're getting the same thing. Right. So for example, let's say we want to delete 75, right? So what do we do? What do we do usually? Do you remember when we delete something, what do we do?
So 38
We
will be the parent node.
Delete.
Yeah, go ahead.
We'll delete 75 and insert 30 in the position of 75 and then heapify downwards.
Okay, so we put this here, you're saying, right?
So 38 will be the parent.
No, 30 will be, no?
38.
Yeah. I'm coming to that. Yeah. 1 minute. Well, is that what we actually do? So you're saying, yeah, so this doesn't satisfy the max property, so 50 should come here, right? 50, 30, 17. And now when I insert 75 again, what will happen? So it was 95, 50. See here itself. No, you're not getting that, right?
Sir, it is not clear. Like, if you can draw it clearly.
Sorry.
Sir, what is in the second position, 50 or 30?
This is 50, 50. This should be 50, right?
Hmm.
For it to satisfy the max heap property.
Yes, sir. So after inserting 75, we have to heapify it again. No?
Okay, we'll heapify it again. Okay, so let's heapify it. So this will be 30, 75. Then this two will again heapify 75 and 50. We got the same thing?
Yes, sir.
So 75 is also ruled out. Right. So now let's check. Okay, now let's check why 38. Okay, now let's check 38. Okay. So in the case of 38, again, we'll do that, right? We'll remove 38, right? Eighty-four, 50,
Again, 30 will be inserted here.
50, 64, 80, 17. Right? And now we insert 38.
And it is already satisfying the heap property.
Right?
Yes, sir.
All right. So let's just try with 50 also, maybe. Yeah, 50 also we will, let's check with 50 what will happen. So 95, 75, 84. Here which should come? For it to be a max heap.
30.
Very good. 30, 70. And now when I insert 50 over here, ये इधर 50 हुआ 30 and it's already a max heap and we get it's the same as this. Right, Aditi? Is this clear? Okay, Snail is saying
Yes, sir.
it will always happen since for a max heap the children for 95 will always be 75 and 84 and so on. All right. Okay. Okay. I hope this is clear. Yeah. Okay, Aditi, you had any other doubt? Any other question?
Yes, sir. 1 minute.
Yeah.
Sir, I am having one, but not in this question, but in the quiz one.
All right. Uh, in Okay, let's finish this quiz 2 first. If there aren't any other questions, we'll move to quiz 1.
So mainly
Quiz one.
questions are
I mean,
from
I was
week
saying
5 to
about
week
quiz
8, no?
two.
Sorry?
So mainly questions are from week 5 to 8. So,
Yeah, for quiz 2, yeah.
okay.
Okay, sir, no problem in this question paper. Only this was the doubtful one.
All
Yes.
right.
Yes,
Okay.
Anushka, you can ask.
Yeah, Anushka.
So I'm having doubt in a different set of quiz 2. I'll be sharing the link.
All right. Yeah. Which question?
So firstly, in question 5, the statement 2. So I want to get a clear idea about the statement. So, sir,
Okay.
in a weighted graph, if all edges are unique, then we cannot determine a unique path from source to destination. That's clear. But what about if we have not unique edges? Can then we find unique path from source to destination?
Okay. Let's see what this question is talking about. Okay. So which of the following statements are true, right? Yeah. Given a graph where all edges have positive weights, the shortest path produced by Dijkstra and Bellman-Ford algorithm may be different, but the path weight would be the same. Okay, so this is clearly true, right? Because
Yes.
Dijkstra's a positive weight has, so Dijkstra's and Bellman-Ford will give the same answer, right?
Hmm. Hmm.
Okay, now the second, given a weighted graph where weights of all edges are unique. Okay, so there aren't any common or all edges are unique. Okay, there will always be a unique shortest path from a source to a destination in such a graph.
This can be possible only in the case of tree.
Okay,
Because
yeah.
otherwise,
So
if you have any another graph like, and we have unique, still like we have unique weights, and it might be possible that we will get two two different ways having the same weights. Like the summation of the weights will be same.
something like this, no?
Yes, sir.
Yes, sir. In this case, all the weights are unique. Still, we are getting two paths.
Is this clear, Anushka? Like this is possible, right?
Yes, this statement is clear to me. I am asking about that if
Okay.
in a weighted graph there is a possibility that edges are not unique, then in that case, what can we conclude about the shortest path from source to destination, whether it being unique or not?
Even if it's not unique, yeah, even if it's not unique, I think it will be, it need not be true, right?
Anything can be possible in that case.
So we
Yeah,
cannot conclude about the uniqueness of path from source to destination.
right.
Okay. Okay, I cleared this doubt. Then next question is question number 13.
Okay, let's look at question number 13. Okay, can't copy this. Okay. In a depth first traversal of an undirected graph G with n vertices, E edges are marked as tree edges. The number of connected components in G is, okay, so it is a depth first traversal. Okay, yeah, what is your doubt?
I could not get how to solve this. I mean, how to think about this.
Sorry, which was the number?
13th.
Okay, so what is it saying? So in a depth first traversal of an undirected graph G with n vertices, E edges are marked as tree edges. The number of connected components in G is, okay. So what is the question? Let's say we have a graph, right? Like 1, 2, it's an undirected graph. 3, 4, 5, 6, 7. Okay, something like this. Okay, now it has n vertices. Now E edges are marked as tree edges, right? So I will do a DFS on this. Okay, I will do a DFS on this graph G, right? So can you tell me one possible, or let's take a path, let's take a tree which will be formed.
Okay.
What will it be?
1,
1,
2,
1 to 2.
2 to 4.
Yeah. 2
and
to
4 to
4.
6. 4 to 5.
4 to 5.
Then 5 to 8.
Okay, 1 minute. 1 minute.
Sir, I think we need
Okay,
to take
1 to 2.
2-3 components at least.
Yeah. Okay, let me just check this. 4 to 5. Okay.
5
Then
to 8.
5 to 8.
8 to 7.
8 to 7.
Then 8 to 9. Sorry, 7 to 6.
7 to 6.
Then backtrack. Then 8 to 9.
8 to 9.
And 4 to 3.
Oh, yeah. Okay, so these are the tree edges, right?
Yes.
And they're asking the number of connected components in G. So, yeah. So what do we know about DFS?
So in DFS, it is like first of all, so Q is for no, it is stack. Yes, it is stack.
It
First
goes in
in,
the
last
depth
out.
first.
Q
So
is
it goes
the
in a
breadth first. BFS.
right.
In DFS.
So if you notice, what is happening is when I visit 1 to 2, right? Then for sure I'm not going to visit any other node in the component. Let's say 1 and 2 is one component, okay? Right?
Yes, sir.
Yeah.
Sir, it is asking for connected components.
Oh, sorry.
Yes.
Number of connected components in G, right?
Firstly,
So
what is connected components?
Here, the complete graph is one component. Na?
Yes, one component.
And that is why, like, sir, we need to take 2-3 more vertices that are not connected with this graph. Then only
yeah.
we'll be able to solve this question.
Yeah, yeah. So, yeah. Yeah, so 1, 2, 3, 4, 5. Yeah, so what this, so, okay, yeah, sorry. So what this means is, let's say we have a graph like this, now 1, 2, 3, 4, 5, 6, 7. So how many components are there in this graph,
3 components,
right?
right?
Yes, that's right. Okay.
Okay. Yes, sir.
So we have 3 components, and if you have to do a DFS on this, right? What will happen? So for example, for this component, you will, let's say if you do a DFS, you will get 1, 2.
You get 3 non-cyclic graphs.
1, 2, 3, no.
Acyclic graphs.
Sorry. Yeah, yeah. Sorry.
So you'll get acyclic graphs for all 3 components, like tree.
Okay.
Total
Right,
6 minus 3, 3.
Yeah. So even in this case, it will be 6 to 7, 6 to 8, and maybe
6 to 7,
sorry,
then 7 to
sorry,
9, no.
sorry, 7 to 9 and
9 to 8.
8 to 9. Right. So what is happening here? For each component, right? We are yeah. So we are not including uh,
Sir,
uh
I have a logic in discussion. Can I share if you?
yeah, sure.
So, sir, generally, what DFS does is it will mark all the tree edges in a particular graph, right?
Right.
So, like if we have a graph which is not completely connected, then there will be a missing edges, the missing tree edges, right?
Hmm.
The tree will not be formed; it will be on a broken tree. It will have different components, right?
Right.
So, first of all, what we will do is we will use the DFS and get all the tree edges for all 3 components
Okay.
and take the number of vertices and subtract them, because we the total number of vertices is always n, and the total number of edges will be n minus 1 in a complete graph which is connected completely.
Hmm.
But in the case of disconnected graph, we will simply reduce n, like we'll subtract n minus 1 from total number of edges and add 1.
Okay.
So
Yeah.
that will give us the total number of components, because here you can see we are missing 2 edges to make this complete graph tree.
Which is
Like which connects the first and second component and second and third component. So we are missing only 2
something
edges.
like this, right? For
Yeah,
example.
we can assume anything. So if
Right.
like there was these 2 edges, then the graph is like we can traverse through DFS and make it a complete tree.
Right.
Just
Okay.
because we are missing these 2 edges, that is why this is not a complete tree. So what we will do is we will subtract this the number of tree edges in these components from the total number of vertices and add 1, because here you can see 2 edges are missing, so the number of components is 3.
Got it. Yeah.
So the formula will become, if we have total number of n edges, then we have to subtract n minus 1, small n minus 1, which will be the number of tree edges, and then add 1. So n minus 1 plus 1. Sir, if you can write, then I will be able to explain.
Yeah. So good. So so the thing is connect. So if it is a fully, let's say it's a connected graph, right? Or if it's a connected graph, then the number of components is how many components will be there?
Connected graph, then only one component will be there.
There will only be one component, right? So,
Yes, sir.
so connected graph of n vertices will have one component, right? And the DFS tree of a connected graph will have how many edges?
N-1 edges.
Is that clear how we got n-1, Anushka?
No, sir.
Anushka, there is a property for trees. Every tree has only exactly n-1 edges, where n is the
Yes,
number of
that I
vertices.
know. That I know. Connected graph has one component. Even I got that also.
Hmm.
But what next?
And so this is a connected this is a connected graph, right?
Hmm.
So in DFS, what we do is, so we have to visit, I mean, in the DFS, the tree which we get finally, there will be an edge from each like a pair of vertices, there will only be one edge, right? That's what traversals do, right? It visits all the nodes once,
They create
right?
tree basically. Yeah.
They create a tree.
Yes.
So for
Yes,
example, in this case, we have just 1, 2, and 3.
n-1 vertices. Edges, sorry. n-1 edges.
Very good. Okay. So it is n-1 edges. All right. Okay. Yeah, Viraj, go ahead. Yeah.
So, sir, here you can see like if we subtract these n-1 edges from the number of vertices, then we will get the number of components in that particular graph.
In that case, we will get -1. No.
How -1? I am saying
See.
n minus n-1. That will become +1.
Okay. Okay.
So what is n-1 here? It is basically e. That is the number of edges.
So what we have to think of in a DFS, right? What it will do is it will
mark all the tree edges.
It will mark all the tree edges of a particular component. Think about it in that way, right? Yes. So,
Yes, sir.
So this is component C1, this is component C2, this is component C3, right?
Yes.
Component C1, let's say it has N1 nodes, this has N2 nodes, it has N3 nodes, right? Got it till there?
Yes, sir.
Okay. So now what is the number of edges in this DFS tree?
n1 plus n2 plus n3 -1.
No. Wait. So this case, no, let's just look at this tree, this graph.
Okay,
Okay,
n1
this is
-1.
very good. This is a connected graph.
Hmm.
Okay. So this is n1 -1. What about in this? So here
n2
also
-1.
N2 -1 and N3 -1.
n3
and
-1.
n3 -1. Okay.
Hmm.
So the total number of edges is this plus
Head.
this plus this, right?
Hmm.
Which is n1
Okay.
plus n2 plus n3 minus
-3.
3. But what is n1 plus n2 plus n3?
Total number of vertices.
9.
Which is 9, which is, let's take it as n based on this
Capital
question,
N.
right?
Yeah.
Right. And so what is this? This is actually the number of edges in the, so E is equal to actually n minus 3.
Yeah, the tree edges in this graph.
So this is actually the number of components in a way, right? Because each time we are getting -1.
Okay, I got that. Now the number of components will be n minus c then.
Yeah.
Yeah.
So that is the logic behind this basically.
E is equal to n minus c. So they are asking c. C is equal to n minus e. Yeah, so thanks, Viraj. That was a good thing, because what in such problems, what you should do is, yeah, take examples like this, right? And try to look for patterns, or try to see, or let's see, in this we just directly looked at what are the examples, and then try to generalize it to something, and you will get it.
Okay, sir. The next question is 16th one.
So what if there is a standalone vertex 10 also,
Hmm?
which is not connected with any of the tree?
Yeah. In that case also, we'll get same.
So do we
let's
consider vertex 10 as a component?
uh,
Because
Yeah,
it is not connected to any.
yeah, we will consider this as a component.
this as
See,
a,
in this case, we still we have n minus, like if you consider the number of vertices, still we have n minus 3 edges here. But the number of vertices is increased by 1. So this time n plus
so it
1 minus
balances.
n minus 3. Yeah.
So it
It will,
balances. No? So this will be n plus 1, and this will be 3 plus 1 minus karega. So it will,
n minus 3, sir. N plus 1
sorry,
minus n minus 3.
n minus. But the number, so, but then we have to consider this also as a component, right?
Yes, sir. But if this will be component, here the number of edges is 1. Let us consider this,
So
the
in the
number of
question, it
vertices here
is
is
asking
n4.
only for the connected components. So do we consider standalone vertex as a component, connected component? I'm asking that.
Yeah, maybe not. Then it's not working, right? This formula won't work.
But so this formula will work now in this case. Why are you saying this will not work? And
Okay.
in many questions, like in the GRPAs, whenever we were given the questions to check the connectivity, we were considering a standalone vertex as a component.
Right. So in this case, there's 1, 2, 3, 4 components, right? But my
Yeah.
DFS number of edges is still the same, right? 1,
Mm.
2, 3,
Like,
4, 5,
sir,
6.
in this case, if you like you use this notation n1, n2, n3, if you consider this n4, like n4 equals to 1 in this case, then the number of edges will be n4 minus 1, that is 0, right?
Right.
But if you apply this formula, then we will get n1 plus n2 plus n3 plus n4 minus 4.
Right. So then it balances off, you're saying, right?
Yeah. Yes, sir.
Yeah. All right. Yeah, Anushka, any other doubt?
Yes, sir. 16th question.
Okay, 16. Let's look at 16. Consider the following algorithm on a connected weighted graph with n vertices and m edges. Okay, sort the edges. Okay, so let's take a graph which has, we have n vertices. Okay, m edges. Is the question visible? Can you all see it?
Yes, sir.
Yes, sir.
Okay. Sort the edges as E1, E2 up to EM in decreasing order of weight. Okay, so we have E1, E2 all the way up to EM. So E1 is the largest weight, right? In decreasing order of weight. Consider each edge EJ in sorted order. Okay. If this edge is part of a cycle, then delete it. Otherwise, keep it in the resulting graph. Okay. So they're saying we take we take a graph and we take the edges in the decreasing order of weight, and we look at each edge. If it is part of a cycle, we delete it, otherwise keep it in the resulting graph. Okay, so let's see what are the options. Let's take an example, no? So it has cycles also, right? So 1, 2, 3, 4. Let's take it as 10, 20, 30, 40, 50, 60. So what is the algorithm? We are sorting it, and we if an edge is part of a cycle, we delete it. Otherwise, we keep it in the resulting graph, right? So
Yes, sir.
in this case, what will be there in the resulting graph? What will
Mm,
remain?
Sir, we can do one thing. We can simply delete all the non-tree edges, because all the there was a theorem, sir said, like all the non-tree edges create cycle in undirected graph. So tree edges will be n-1 and total number of edges is n. So m minus n-1 edges we will delete.
So
Okay.
here what we will delete?
30 and
So
60.
yeah, according to the algorithm, what will you delete in this example?
30 and 60.
But I think 10 shall be deleted because it is in the, what to say, decreasing order.
Decreasing order, then we will start with 60.
So
Yeah,
it's
we'll start
that
with
for that
60.
reason 10 shall be deleted.
Yeah, you are right, Anushka. Like 60, first of all, we'll add 60, then add 50, and add 40. And then we'll move to 30. So 10 and 10 will be deleted.
Very good. Okay. So the algorithm says, okay, so I keep 50, I keep 60. Is 40 part of a cycle? No. 30. I keep that. Now I look at 30, right?
Yes, sir.
Is 30 part of a cycle?
No, sir.
It's part of this cycle, right?
But so now it is not, no. The time
Oh,
we will
sorry,
reach
sorry. Oh,
10.
yeah, yeah. Sorry. Yeah, sorry. Yeah. So right now it's not part of the cycle. So is that what the question is saying? If this edge is part of a
It is a bit unclear for me that is it told by question or is it expected from question?
The thing is, sir, the question is not complete actually.
Yeah, I'm getting it. Yeah. So should we? But my understanding is consider. So we have to look at this
It is
graph.
not clear if we have to look the original graph or do we need to construct the graph in that order.
I understood. Yeah. Karsha is asking, does part of a cycle does it mean the same as creating a cycle? Yeah.
That is not clear now.
For that, there
So
are total 3 cases. 10, first we remove 10, after that 20 and 30. The total number of cases are 3.
Yeah, so this word, no, part of a cycle, I think that means that we have to look at this itself. Otherwise, what would the question be if this edge creates a cycle?
So the thing is, this question is not complete, like according to the if we think algorithmically. So that is why we have to attempt this question theoretically. using
Okay.
the graph entry properties.
All right.
So
Okay.
that was
So my yeah. No. So my understanding is yeah. So my understanding is if we have to look at this part itself, okay, and see if there is if it is part of a cycle, then we don't yeah, instead of yeah, we can actually delete it from here, right? And it won't be there in the resulting graph also.
anyhow, sir, we have to remove the edges. So we can use both any of the approaches. Like we can start building the tree, or we can check with the original graph. Both way we will get same answer.
Yeah. So in this case, we will not keep 30, right? Because it's part of a cycle.
Yes, sir.
Getting it?
No, sir.
Okay.
Why shall we not do this thing with 10 or 20? Why just 30?
Listen, Anushka, there isn't like the question is saying we have to check how many edges should be deleted. We are not creating the graph, or we are not considering any of the graph. We can use any of the approaches. The thing is, we need to tell the like how many edges we can delete. That's the thing only. So don't confuse with like 10 and 20. This question is not complete algorithmically.
So either of the edge of the cycle can be deleted being 1 in number.
Yes.
Yeah. No, but some of the options, if you see the ones below, what remains at the end is a minimum cost spanning tree. Now
It is
for
connected and spanning tree, minimum cost spanning tree, that is the clear thing. But what about others?
no. So then if you want a minimum cost spanning tree, if you want this option to be true, then you should consider the weights also, right?
Yeah. Then in
Then
this
we
case,
have
then
only
this question
30.
is not complete.
So
Well,
we
if
will
you see,
remove only 30 in this case.
yeah. So just follow the algorithm, no? We have sorted the edges in decreasing order of weight. We consider each edge EJ, right? And if it is part of a cycle, we delete it. Otherwise, we
So,
keep it.
sir, in this case, we will first encounter 30, then 20, and then 10. So
Right.
then we will delete 10 only, no, because we encountered it at the end and we found that 10 is contributing to the cycle.
But we need minimum spanning
30
tree,
is
so
also
we'll
part
delete
of
30.
cycle. We will delete
It is
30
not
first.
given that we need it.
It is not given, but it is like that is why I'm saying the question is not clear in itself.
So it is
So
clear, like it is a part of cycle. 30 is a part of cycle, and we are going decreasing order.
yeah, yeah.
You
So
will encounter 20 and 10 after 30. So how can you say
exactly.
that 30 is part of a cycle?
No. So I think you got confused. So don't. We are not constructing the graph again. The graph again. Okay. Nowhere is it saying that construct a new graph. Got
Yeah,
it?
we are not
Yes, sir,
creating the
but we
graph.
are considering the weights from that E1, E2 uh, sorted weight,
Exactly.
no? So
Exactly.
in that thing, we will have the weight of 30 before 20 and 10.
Acha,
Right.
Anushka, let's
Right.
do one thing. Let's start. You have to consider this graph only. First of all,
Hmm.
we will get 60, so we'll
Hmm.
add 60. Then
Okay.
50.
Yeah. Another thing. Let's consider how are you going to represent this graph? Let's say as an adjacency list. Okay.
Okay, sir.
Right.
Okay.
So it will be 1, 2, 3, 4, 5, 6. And each of this will have some way, let's say it has the weight and the edge and the weight, right? So this, what will 6 have? 4 comma 6, sorry, 4
4
comma,
comma 60.
okay.
60.
5 will have,
4 comma 50.
yes. 4 will have,
3 comma 40.
5, comma 50,
5 comma 50.
6, comma 60.
3 will have,
1, comma 20, 2, comma 30. 4,40, 2,30, 4,40.
Okay.
2 will have 1,10
1,10.
and 3,30.
1 will have
1 will have 2,10 and 3,20.
Yeah. Now, each of this is in sorted order, right? So yeah, so this will be my
But so not in
E1.
the desired sorted one. No? It is in not. It is in ascending order rather than decreasing order.
It is in descending order basically.
Yeah, it's
Descending
in
order
descending
starts
order.
from largest to smallest. No.
Yeah,
Exactly.
so it
Yes.
is starting from largest to smallest.
60, right? We'll start with this one.
Oh, yes, sir. Then 40, 30.
Yes, sir.
Okay.
Yes, sir.
Now, yeah. So the algorithm is saying, okay, now we'll consider E1. It is not part of a cycle. We won't make any changes to my adjacency list. Okay. 50, this edge not part of a cycle. Okay, we won't make any changes. 40, it's not part of a cycle. We won't make any changes. Now, this E4, it's part of the cycle.
We'll
Yes,
make
sir.
change.
Right,
See,
Anushka?
Anushka, the graph is already there and we are only checking cycles.
Consider the decreasing
Okay.
order.
Okay.
Sorry, Divakar?
Prash was saying something.
Oh, sorry, Prash. Yeah. So since
Don't
this,
we have to consider the decreasing order?
yes,
We are considering a decreasing order now. 60, 50, 40, 30.
So 30 will come first, then 20 will come, and then 10 will come. If 30
Yeah.
comes first, we pick 30, then 20 comes, and then 10 comes. Now 10 is part of a cycle, so we remove 10. We don't
no.
remove 20, 30.
No,
We are not
we are
making a
not.
graph.
Yeah, we are considering this
It is
graph
already,
only.
yes. So we will remove 30 only in the question.
So they, like we have given this adjacency list. So if we check E4 on this E4 30 weight edge, and it is in cycle. So we'll delete
Yeah,
it.
so it is part of actually 3 and 2, right? So ye wala and
Sir,
ye
but
wala.
the first in the algorithm,
Hmm.
sir, am I audible?
Yes.
Yes. Who is this?
Sir, in
Sorry, I
the
can't see.
algorithm, the first step says sort the edges as A1, A2 in decreasing order of weight.
Yeah.
So if I considering the decreasing order of weight, then every time I pick it will be the maximum value among edges in a cycle. For minimum cost spanning tree, we first consider the smallest, then we go for next smallest layer.
Yeah. Okay.
But here we are considering the order decreasing order. So first we consider the maximum is 3, then 50, which doesn't, then 40. Then we will
Right.
consider 30. Now 30 will be a part of our actual answer. Now we will choose 20. Then it will be part of our answer because it will not form cycle. Then 10 comes. Then I won't choose 10 because it will form a cycle. So it is not forming the minimum cost spanning tree.
No. Just see what we are doing. We are not, once we encounter E4, this thing, we are deleting it from the graph.
Sir, but what I will say is
But
like,
sir, we are
this is the,
picking in sorted order, right? We are picking
Yes.
every edge in sorted order. So how can we say that if we pick 30, it is forming cycle? Because we haven't encountered other edges yet, because we haven't
We
encountered
already
20 and 30.
have
20
all
and
these
10.
edges in the graph. That is why we are considering this adjacency list. We already have all
From the
the graph
graph, we
created.
can even delete that E5 and E6 also, because it would also contribute to the cycle in the graph.
Yes, we can, but we are moving in decreasing order, na? So
Then
first of all,
also,
we will listen. Like first of all, we will see 60, 50, and 40. We will not delete them. Then we will come to 30, and we will check in our adjacency list if 30 is creating cycle or not. Here you can clearly see 30 is creating cycle because we are not constructing the complete graph. We are checking the graph that is already being created.
and then from that graph we are deleting.
Yeah.
Yes.
But still, sir, the question is not like correct because we
Yes.
are considering this example only.
It's
What if we
incomplete.
have any another example? Then in this order, it is not sure that we will get the minimum spanning tree only.
We can take another example also. I mean, short example.
Yeah, we can construct a 5-6 edge, and clearly we can see that it is not the case, and we will always get the minimum spanning tree.
So can we have an example where we have more cycles?
Yes,
I mean,
sir.
so that it's very clear.
That would be more
Cycles.
clear one.
Sure. Okay.
Take five vertices. We can draw cycles.
Okay. So let's take like is this fine?
Yes, sir.
Okay, what should
And
the edges be?
for the weights, we can make the difference between the two vertices. That should be a good idea.
Okay. So for example, this can be 10. This can be so this 10, 20, 30. Will this work? 30, 40, 50, 60, 70.
So since the graph is very small, I'm not able to differentiate the which edge belongs to which weight.
Okay.
You can at least write it nearby. You can write it nearby. 1.5 as 20 or something, whatever.
Okay, so okay, got it. Yeah.
Only the
So
inner
you
edge.
can draw a bigger graph, like making this. You can full screen this whiteboard and create a big graph.
Yeah, sure, I'll do that. Okay, let's try 1, 2, 3, 4. Let's form one cycle here. Let's form one cycle here. Let's form. Is this okay? Or I'll add one more.
One more. So one more can be.
2 to 5. Yeah.
Yeah, this is also enough.
Okay. So for this cycle, let me take then for this, let it be 90, 100, 10. This is, let's take it as 70, 50. Okay, so according to this algorithm now, which will be the first edge which is chosen?
The one with the maximum weight, right?
1, 3 edge with weight 100.
1 to 3, the 100.
Okay, So this will be deleted.
Yes, sir.
We can
It's
ask
for,
questions to the people who were having doubt. Anushka and one more person, right?
Yes.
Anushka, can you help, sir?
About writing the list.
no. You remember the algorithm, no?
Yes, sir.
So the algorithm will take all
Algorithm.
this in sorted order. So first will be 1, 3. Okay, let's list it down. Yeah, 1, 3. Then
Yes, followed by 3, 2.
okay, 2, 3.
Then 3, 4.
3, 4.
1, 4.
1,
2,
4.
4. 4, 5. 5, 3.
Hmm.
And
And
then
1,
1, 2.
All right.
so we
Okay.
have 8 edges. Yes, sir.
Yes, sir.
Yeah. Okay, very nice. So now like remember, think of this like a while loop, and we are iterating through these edges, right? So we come here, we check. Okay, what is the question to check?
Is it a part of a cycle?
Part
Is it
of
a
the
part of?
cycle, then we will delete it or else we will keep it.
Yes.
Right. Okay. So the question at this point at this point we just have to check whether 1, 3 is part of a cycle.
Is it a part of cycle, Anushka?
Definitely it is.
Okay, then we can remove that, right?
Hmm.
So can you remove?
Yeah, I won't erase it. So just imagine we have removed this. Okay.
Okay.
So this will be removed from the graph. Okay.
We move to the next stage.
Yeah.
Which is
It is
2,
also
3.
the part of the cycle.
So we should remove that also.
Yes.
It is part of a cycle, right?
Yes,
It
sir.
is part of this cycle, right? It's part of this cycle.
Yeah. Yes, sir.
We'll remove it. Okay. So and this
What
is
about
removed
3,
from
4?
It is also the part of cycle.
3, 4 is part of this cycle, right?
Hmm.
So we remove it.
1, 4 is also part of cycle.
1,
Yes.
4,
Yes.
it is part of this cycle, right?
Hmm.
Yes. We remove. Okay. 2, 4.
It's not a part of cycle anymore.
Yes.
Okay. So
We
2,
will
4.
keep it.
We'll keep it. But for now, Naj, for us to understand it properly, I'm just redrawing it again. Now we are not creating a new graph. Okay, just to be clear. Okay. This remains. Okay. Now 4, 5.
Not a part of cycle.
Not
So
a
we will
part
keep
of
it.
cycle. So we keep it. Okay.
3,
5,
5
3.
is also not a part of cycle.
Okay.
We again keep it.
Okay. And 1, 2.
Is not a part of cycle, so we'll keep it.
Okay. Right. So, yeah. So from this, yeah. Go ahead.
No, so
Someone
you
else?
go. You go.
All right. So some things are coming out, right? Like if what we are doing is at each step we are checking if it's part of a cycle, right? In a way, we are checking if it is forming a component, right? If it is, we are somehow removing that edge, right?
Yes, sir.
Okay. So yeah, now let's look at the options. Sorry, which was the question?
Question number 16.
Okay. So
So,
yeah,
Anushka, which option you have uh, the doubt?
I'm clear about minimum cost spanning tree.
Okay.
Then about C option that it is connected graph. Definitely it is. I'm not
Right.
clear
Okay.
about the first option, A option.
Only the first option, right?
First option
Yes.
I already told you, like
Now,
we have to
we
keep.
take this example also, Viraj, right?
Yes,
Hmm.
So
sorry.
m minus
Please
n
do.
plus 1. So that is what we need to check,
Okay.
right?
So you are
So
we
how
are
much?
checking this with the example, right?
Yeah, yeah.
Yeah, sure.
Okay.
So here m is actually 8. 8 edges we are having.
We are having 1, 2, 3, 4, 5, 6, 7,
Yes,
8.
8
Okay.
edges.
8 edges, right? And what is
Hmm.
n? N is the number
N
of
is number
nodes.
what is
Vertices, correct. So how much is that?
5.
5.
5. Great. So according to the formula, what was that? M minus n
N.
plus 1.
Plus 1.
Or the number of edges which are deleted. Am I right?
Yes. Yes.
So what is that? 4.
Yes.
8 minus 5 plus 1 is what? 4, right? Understood?
Yes. 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 Yes.
And through our algorithm, how many edges did we delete?
Mm, 4.
Delete 4. Equal?
Yes.
Yeah, another way to think about it is, see, since we have since what we are getting is a minimum cost spanning tree, how many edges will that have?
N minus 1.
How many?
N minus 1.
Minus 1.
Very good, very good. So it will have n minus 1 edges, and we know that our
Oh, and then total number of edges minus N minus 1. So it being M minus N plus 1.
Exactly.
right. So once you do this example and then
Hmm.
you understand that it's a minimum cost
Yes.
spanning tree,
And it is
right?
connected
Then
one.
yeah, all the other options, automatically follow,
Yes.
right?
Yes, sir.
Got it, right?
Yes, sir.
Okay, sir. Done.
Oh, all right,
Yes.
thank you. Okay, any other questions?
Not now.
Okay, so don't worry, tomorrow's session is also
I
there.
I will
Yeah,
solve quiz 3 questions and then get back.
all right. All right. So don't forget about week 11. It's there for the final uh, exam, right? So uh, yeah, so week 11 is something a little different from what you all have learned before. And I hope all of you will be happy. There are no there are no GRPAs or practice
Yes.
problems for week 11. Okay,
More of
so
a linear programming kind.
yeah, yeah.
So do we have week 12 also?
No, week 12 is just revision. Yeah, there's no, nothing new will be introduced in week 12. Yeah.
So you can at least add practice programming assignments for week 11.
All right.
We have enough till week 10.
I think you all have enough till week 10. And the concepts in week 11, no, it's not for you all to actually do programs related to that. Of course, you can do that. But the concepts are more to give you an understanding of, what are the limits of up to which we can write efficient algorithms, right? And you will be surprised to know, and or if you see the lectures, you will see that there till now we have looked at problems which are in order n log n, n square, n cube, right? And we considered them as somewhat efficient algorithms, right? But there are some problems which look very simple, right? But uh, till now we haven't found any efficient algorithm. So what do I mean by an efficient algorithm? An efficient algorithm is something in the form of n to the power k, where k is a constant, right?
Polynomial form, basically.
Yes, in the polynomial form, right? Uh, right? So all the algorithms which we discussed till now, right? It is either n log n or n to the power k. We have gone up to n cube, I think, right? But there are some algorithms, some problems for which till now we could not get a polynomial time upper bound, right? The worst case complexity is exponential, right? Of the form some like, sorry, 2 to the power n or something like that, right? So those are the type of problems which uh, yeah, which will be discussed in week 11. There are, of course, other types of problems which Sir discusses, linear programming and network flows. So I'll just maybe, yeah, we have around half an hour left. I'll just quickly give you some ideas about, what this is, right?
So, sir, I've used the same concept also in the Aadhaar card example, to the power n.
Yeah, yeah, right. And you know that that 2 to the power n, right? Um, it is exponential, meaning it for very small inputs also of n, right? It just blows up, right? And things like 2 to the power 100, I think sir has mentioned that also, right?
Yes,
2 to the
sir.
power,
They also shows the speed of Python and other languages.
sorry, the speed, right. Yeah. So all that you all are familiar with, right? And uh, yeah. So yeah. So maybe I won't talk about metformin. So someone had some doubt regarding reduction, no? Someone was saying something.
Viraj.
Yeah,
Yes,
Viraj.
sir.
Yeah.
I want I didn't explain completely the bandwidth allocation, the reduction, like we reduce it to network flows, right?
Yeah. Okay. All right. Uh, yeah. So for that, I'll have to explain network flow. Okay. So yeah. So okay. So let me explain network flows quickly, right? Yeah. So what network flow is that you start from a source, right? And you have a destination T, right? You want to transport something from S to T, right? And it's a graph, and there are several edges, right? And each of them have a weight, right? And this denotes the maximum amount of things which can be transferred from any two edges, any two nodes, right? You can think of it as pipes or something which has a capacity, right? So this tells me that from S to A, I can transport, let's say, maximum 3 units of a particular thing, right? And yeah, so the question in this network flow is what is the maximum amount which can be transferred from S to T such that it satisfies these constraints. One is uh, any of this cannot exceed the total weight of a particular edge, and that is called the capacity. And the second constraint is whatever is incoming, the same should be outgoing, right? The sum of all the incoming edges should be equal to the sum of the outgoing edges. So for example, here, let's say if we take this as 3 and if we take this as 10, right, full capacity, if we flow to A, okay, so we have 3 plus 10, which is 13, which is incoming, but you will see that only 2 is outgoing, right? So from A to D is the only way you can go out from A, and you can only push out maximum of 2 units, whatever it is, right? So definitely we cannot take 3 and 10. we might have to take some other combination such that maybe it sends a maximum of 2, right? So that is the network flow problem. And the question which we ask is the network flow algorithm will tell us the maximum flow which can go through this through a given network. All right. So, right. Okay, on this. Yeah, and this algorithm is known as the Ford-Fulkerson algorithm, right? And it is a way which helps us calculate, which path you should take and what is the maximum flow which is possible. Okay, so maybe I'll just quickly Viraj, you have a doubt in the actual algorithm?
Yes, sir. How to reduce this bandwidth allocation to network flow?
Okay, all right. That we will do, but I'm just thinking. No, but let's say I give you an example of this. You know how to calculate the max flow?
Yes, sir. Using this Ford-Fulkerson algorithm?
Yeah.
Yes, sir.
All right. Yeah. So basically what this algorithm tells us is that it is somewhat like, somewhat similar to dynamic programming where you try out one thing, but if it doesn't, or, if it is not the optimal way, then you backtrack and you do some things, right? So let me see. Okay, so the algorithm is explained, so I won't get into the details of that. So now an important concept in week 11 is, let's say you have an algorithm, right? How can you translate that algorithm into, or that problem, sorry, not translate an algorithm, translate a problem into another problem. All right. So here in this case, you can see this is a very clearly defined problem of you start from a source, you go to the destination, and you have uh, edges with some capacities, right? Now, okay, where was bandwidth allocation? Okay.
And sir, it will be better if you can explain this example once again.
Okay. All right. So here let's talk about network flow.
No, sir, not the network flow, but this example only, like how bandwidth is allocated.
Okay. So
This example is not completely clear to me, actually.
yeah. So actually, yeah. So here actually, sir didn't actually give an algorithm, but what he said is this can be reduced uh, to a linear program, right?
Yes, sir. But we cannot reduce it to linear programming always because we can have a large network.
Exactly. Right. Right. So yeah. So this is an important part, right? Of, let's say we have a problem. We want to actually first translate this problem into a model for which we can apply an algorithm, right? And so in this case, this is a bandwidth allocation problem where, if you see, it is somewhat similar, right? It tells me that these are the maximum capacities, right? And Yeah, these are the maximum capacities which can go through, let's say, these wires, right? And uh, yeah, and what they're saying, each of the connections A, B, BC, and AC should have at least 2 Mbps of bandwidth, right? Yeah. And of course, you can have direct connections or indirect connections. So if I want to connect A and B, I can go like this directly, or I can go like this, right? So
Yes, sir.
what, sir? Yeah. So this is very specific to this example. What, how sir has modeled it is, the path from A to B directly has been modeled as, I think, XAB, and via an intermediate node, let's say C, that path is YAB. Okay. So yeah, so that's what, so via the short connection is AABB, which is AABB, that is XAB, and via the long connection is YAB, right? So similarly, for each of the other nodes also, you will have two connections. Sorry, two paths, right?
Hmm.
And if you recall the linear programming model, we have we have some constraints, and we have an objective function which we want to either maximize or minimize, right? So okay, let's take this example. No, so if we want to convert this into a linear programming problem, what we have to do, we have to first of all, uh, yeah, we have to translate these into constraints, like which sir has done, right? So what it is saying is, uh, so what is XAB? XAB is this. So in a way, which all paths are possible?
From
Yeah,
A to B,
XAB.
two paths, and from C to B, two paths. Total four.
So there are total four, right? So 1, 2, 3, 4, right? So, and all of those should be less than or equal to 10, because this is the maximum capacity for this link, right? Similarly, for between A and C, then B and C, right?
Sir, there should be three more conditions, like for these 6, 11, and 13 edges, right?
Okay, what should the condition be for that?
Like, sir, here we are writing these, like the sum of these four things should be less than equals to 12, because the
Hmm.
maximum capacity here is 12.
Hmm.
Similarly, in the case of small a to small b edge, the maximum capacity should be 6 only.
Yeah, that's missing. Yes. So I don't, that's here, right?
Yeah.
Yeah, right. So in a way, for each of this, we give constraints, right? And finally, yeah, and that pairwise also, it should be greater than at least 2 Mbps. So that is another constraint. So you're realizing, right, for a simple problem like this, you see that so many constraints have come. Simple, I mean, a simple graph like this, so many constraints have come up, right? And so if we keep on adding edges and you keep on adding nodes, right, then this will blow up, right? It will become exponential very quickly, right? So the basic idea which sir wanted to convey was, it is possible to translate one type of problem into another type of problem, right? So this this bandwidth allocation thing has been translated into a linear program, right? And you maximize, this is what you want to maximize, and simplex will yield something, right? Yeah. So it doesn't scale well, right? Yeah, Viraji, what doubt did you have exactly?
So how to reduce this to network flow?
So
Like in network flows, we have two things: source and target. We have to reach from source to target. But in this bandwidth allocation problem, we can have like so many users and so many hubs. So how can we like exactly translate this problem to network flow? Or like do we need to like consider each like pair of users as a source or a target? Like in that thing only I'm confused. That is the confusion.
yeah, even I think that is how we should do it, because yeah. And another thing is, both of this is bidirectional, right? Like
Yes,
10
yes,
can
sir.
flow here, 10 can flow here, right?
Yes,
So
sir.
this is like this is like this. Yes. So this is like this, right? So then if we consider that, yeah, so
Why, like I was in the confusion because if we use this network of problem again, we are in a like big mess. Everything will be like confusing how to like convert it to network.
yeah. Yeah, but I think, yeah, as you said, maybe we can consider a variation of this by maybe just looking at, what is the,
Pair of yeah,
yeah,
a single
between
pair.
A and B. Yeah, between A and B or A and C. But then will it work if we combine all of them together? No, right?
But combining them, like taking each pair in a like graph which is too big, it will be like a very worse solution actually.
Hmm. Right.
And sir, one more thing, we cannot combine those solutions actually because like consider a case like I took
No,
A and
yeah,
B.
we can't because yeah, it's not a simple combination, no? Because
Right.
the variations will happen across pairs, no? It won't be
and
the same flow. Yeah.
and the weights are limited,
Hmm.
so it is not possible to combine.
Yeah. Uh, yeah. So I'm also not getting it. I don't know how we can directly translate this to a network flow problem. And I don't think it. So let's say if we add a new node also, it's not working. Hmm. If we add a new node
So
S,
like linear programming, this problem we converted into like linear programming. Similar way we can convert a small graph problem in network flow, but for big problem again there is a problem.
yeah. I agree. Yeah. Network flow, the main property is you need a source and you need a sink,
Yes, sir.
and as long this the graph in between S and T, it can be very big. That doesn't matter, right? The network flow algorithm will run, efficiently. So
Like,
that
sir,
we don't. Yeah,
one more example, sir, took in the slides, like the teacher, like instructor and course example, something like allocating the students, the instructor. So in that case, we can convert it into network flow because we can consider any source and any target. But in this problem, we'll have like many users, so this cannot be converted easily.
right. Yeah, even I agree. Yeah. All right. Okay, others, are you all confused? So this type of problems, which you will see that so if you all don't know what all this is, it's okay. But what we actually did was we took one problem, this bandwidth allocation problem, and translated it into a linear programming problem, or we also tried to translate it into a network flow problem, right? So these are known as reductions, okay? And yeah, so this is the example which Viraj was talking about. See, this is known as a bipartite matching problem, where you have, let's consider this as a kind of a graph kind of structure, right? Where you have teachers who can teach certain subjects, for example, and the arrows denote the preference which they have. For example, Sheila can teach history, Dev can teach English and history, right? And the bipartite matching problem states, can I find a matching which respects these preferences, and can I get a good matching, right? So what can be done is this can be converted into a network flow problem, right? Where you just add a source and you added a sink and connect the source to all of this, right? And connect the sink to connect the things on the right to the sink, right? And yeah, so and assign weights of 1 here, right? And assign weights of 1. So what does this tell us? So this tells us that for, let's say, this node Sheila, a flow of 1 is coming in, right? So a flow of 1 can only go out of it, right? Or if I take an example of Dev, a flow of 1 is coming in, and notice that there are 2 arrows, right? And I cannot do 1 and 1 here, because then it is violating this constraint of whatever is incoming and whatever is not equal to whatever is outgoing, right? So in that way, what this tells us is that since the incoming is edge has weight 1, outgoings should also have exactly 1, right? And the other way also, right? So let's say we allocate uh, we allocate maths to Priya and to Kumar. Okay. This is incoming is 1 plus 1, which is 2, but outgoing is only 1, right? So that is not a correct allocation. So by adding these weights, by transforming this into a network flow problem,
Sir,
right? Yeah, Viraj, go ahead.
so we must add like weights to all these edges also, like the instructor to subject edges. We have to add constant weights to all these edges, right? Then only this will be converted into network flow problem.
Yeah. Sorry. Yeah. I mean, Yeah, all of this should be 1, 1. Yeah, all of this should be 1. Yeah, correct. Sorry, yeah, I missed that. Right? Yeah. So, so what we have actually done is we have taken the bipartite matching problem, right? Did some modification, rearrangement, whatever, and translated it into a network flow problem, right? And what we'll do is we'll actually, the network flow will actually tell us, you know, how actually it should flow. For example, it will say Sheila is assigned to history, Aziz is
Maximum
assigned to,
allocation.
yeah, say Priya
Okay.
to biology. Okay, so it will give us all these allocations, right? Maximum allocations. So some can be zeros, right? Like this will be 0, but the others will be 1. The ones which are 1, so for example, Aziz physics, Priya biology, these are the actual allocations, right? So by solving the network flow problem, we have actually got the solution to bipartite matching, right? So we have, let's say, the bipartite matching problem, right? What we actually did is we did some transformation to the bipartite matching problem. We translated it into the network flow problem, solved the network flow problem, and the output which we got from the network flow problem, we translated the output to get to the solution to the bipartite matching problem, right? And notice that this will work for all bipartite matching problems, right? Network flow will give some solution, and you can now use that solution to solve the bipartite matching problem. All right. And in the later lectures, what you will see is that the you can think of it in the other way also, right? So let's say if I don't know how to solve a problem X, okay, and if I know yeah, so if I don't know how to solve a problem X, right, and if I can reduce X to some or if I can take a problem Y, right, and reduce it to X, right, and if there is no good way to solve problem Y, then we can be sure that there is no good way to solve problem X also, right? So that is yeah, that is explained in lectures 6 and 7, right? We don't have time for that, right? So where you take one algorithm, right? You take one algorithm and reduce it to some, or you take one problem and reduce it to some other problem, right? For which you have a solution, right? This is exactly what we did. We took the bipartite matching problem. So we want to know the solution for the bipartite matching, right? What we did is we did some pre-processing, like we added the source, we added the sink, and we added weights here, all that pre-processing we did. And this is the network flow algorithm, right? Which will give us the flow. We do some post-processing to get the output for the bipartite. Okay, so yeah, so this is, and you will see that this is a very common practice in algorithms, right? And the other way around of, let's say you don't know how to solve a problem, or there isn't an efficient, it's not that you don't know, there isn't an efficient way to solve a problem. If you can take some other algorithms for which we know there is no efficient way to solve a problem and reduce it such that it reduces to this problem, then we can be sure that there is no efficient way to solve this problem as well.
Sir, can I ask something?
Yeah, sure.
Sir explained about the non-deterministic polynomial time. So, sir, what is the meaning of these keywords after NP, like NP complete, NP hard, NP incomplete? Like complete, hard, incomplete, and some keywords are there after these.
Yeah. So where is that? Yeah. So what non-determinism means is that we really can't say, so there are multiple approaches, or there are multiple ways to get the answer, for example, right? And we really don't know which of them is, or we cannot deterministically, or from the start, we cannot say which of the approaches will give us the right answer. Okay, this is a very naive way of saying it exactly. So, so that is the meaning of non-deterministic, right?
Yes, sir.
Where, so what is NP saying? NP is saying that you have, so you have a checking, so you know what a checking algorithm is, right?
Yes, sir.
Yeah, maybe I will.
So, sir, NP simply means that we cannot, like, there is a problem and we cannot determine that problem in polynomial time. The efficient solution for that particular problem in polynomial time. So that those problems are called as NP problems. And sir, what is the meaning of these keywords like hard, incomplete, and complete?
Yeah, so NP complete, I can tell you. So NP complete is, or maybe I'll take.
And sir, I have one more doubt. Like in the lectures, sir said, and like polynomial time problems are subset of non-polynomial time problems, right?
Why is that the case?
No, sir. Yeah, why is that? Like NP problems are those like we cannot solve them. Then there is a subset polynomial time, which problems like those problems can be solved, right? So why is P is subset of NP? P can be solvable. So these should be disjoint, I guess.
Okay. Okay. So, so the question is, so now what we are looking at is different classes of problems. Okay. And till now, what we have seen, all our polynomial time algorithms are solutions, are the algorithms which are in P, right? They are algorithms which can be solved in polynomial time, right?
Yes, sir.
And what is NP? NP are we do not know of efficient algorithms which can solve an NP problem in polynomial time, right?
Yes. Yeah.
But we have an efficient checking algorithm, right? Which runs in polynomial time.
Yeah. So efficient checking algorithm is basically like we cannot like solve the problem, but we can check the problem if it is correct or not, right?
Exactly. Yes.
So this is for only NP problems. We can check NP problems easily, but in the case of P problems, we cannot check them easily, but we can get their solutions easily.
We can check them also easily, no? P.
Yes, sir. Professor said this thing, like the checking of P problems, like the solution of P problem is comparatively easy. Like the proof, if you want to prove them.
Correct.
Proof of correctness of algorithms, basically.
Or even solving it, right? Or even solving it. So if you can solve a problem efficiently in polynomial time, then you can also check it in polynomial time.
Yes, sir.
So all problems which can be checked in polynomial time are in NP.
Which can no, sir, are in P, na?
No, what does NP say?
The
NP,
problems which cannot be solved in polynomial time.
that is
Non-deterministic polynomial time. No?
yeah. So what it is actually saying is that so it is just telling NP is just telling us about the checking algorithms. Okay. So I think that's where your confusion is. So we do not know if there is a polynomial. Algorithms in NP. Okay. Till now we do not know if there is an efficient polynomial time algorithm which can solve a problem in NP. But we do know that there is a checking algorithm which can polynomial time.
Sir, I am like getting more confused now.
Okay. Yeah, tell me what is your point. So I think what you're saying is whatever is in NP, you're saying it cannot be solved in polynomial time, right?
Yeah. Like we cannot determine the problem in polynomial time.
Yeah. So that is the issue. We really don't know if that is true or not.
But we are considering that it like most of the people are trying from this year. So we are saying that we cannot solve this because until today it is not solved.
Yeah.
So sir, why is this like P subset of NP? P and NP should be disjoint, no?
Right? This is why you're saying it, right?
Hmm.
So one thing is we really don't know if, let's say, there is an algorithm in NP, we cannot 100% say that there is no polynomial algorithm which can solve this problem. For example, this is a problem. Okay.
Yeah, so now I got it.
So saying that if we keep it disjoint, we are saying that there is, we know for sure that there is no polynomial algorithm which can solve this problem.
Okay. So that means, sir, you are saying till now we don't have any proof to prove that NP and P are disjoint. So that is why we are keeping them as a subset.
But the other property of NP also you should remember, right? Which is NP has an efficient checking algorithm which runs in polynomial time.
Yes, sir. We can efficiently check the solution of NP problems if it is correct or not.
Right. But we can also do the same for P problems.
Yeah.
So keeping both of them disjoint is not correct, right?
Yes, sir. It will contradict in this case. Yeah. Unless we have a like robust proof for this, we cannot say anything about it. But that's the case. that we can check their efficiency, and that is why we are keeping it as a subset of NP problems.
Correct.
Okay, sir. Now it is clear. Thank you, sir.
All
And
right.
sir, what about these like NP harden and NP complete? Like, what are these problems?
So like the we can ignore for now, but I'll talk about NP complete. So so NP complete also is a subset of NP. Okay, and of course there are two properties. One is X belongs to NP. Okay, so so when it belongs to NP, what do we know? We know that there is an efficient checking algorithm which runs in polynomial
Polynomial.
time, right? And
Yes, sir.
one more important property is that for all y, so let's say for all the problems in NP, right, whatever NP is, right, that all those problems should reduce to
Yeah, because this is a class of NP problem. So there was a theorem, Cook-Levin theorem, that we can reduce all NP problem to some problems. Like there was a Boolean satisfiability problem.
Yeah.
So we can reduce the independent set vertex cover to that particular problem.
right. So what this is saying, for all y which is there in NP, you have to reduce, if y reduces to x, then x is an NP complete problem, right?
So Boolean satisfiability is a NP complete problem.
Right.
Okay, and sorry, the independent cover problem is not NP complete. This is in between, like NP complete and P. Only the NP class problem, right? So, sir, you are not audible.
Can you hear me?
Yeah. Yes.
Hello?
No. Yeah.
Yeah.
Now clear.
So independent set is also NP complete, right?
Sir, but we can reduce it to Boolean satisfiability, na?
Yeah.
Still, it is NP complete.
Because it reduces to SAT, right? So it is NP complete.
But sir, you are saying X is NP complete. Like, if some problem Y is reducing to some problem X, then
Right.
X is NP complete. Not
Right. Not the other way around.
Yeah. So in this case, Y is not NP complete. X is NP complete.
X is NP complete, correct.
So let us consider a case Y is independent cover and X is a set. Boolean satisfiability.
No, X we know is already in NP complete, right? So you want to say what is Y? Let's say no. So let X be the independent set, right?
No, sir. Take X as SAT set.
Okay. Let me take X as set. Okay.
Yeah.
X as set. Okay.
And take Y as independent cover.
Okay.
Independent sets. Right. Yeah.
Okay. IS curve. Oh. Okay.
Now, in this situation, according to this example, like theory that you have given, the SAT problem is NP complete problem, right?
Yes.
But what about Y? Like, will it belong to NP or it will belong to NP complete, or it can be either?
Yeah. So that's why I said we should actually take X as the independent set problem, because that's what we want to check, no?
Yeah.
Right?
Sir, but we want to reduce Y to X, and X should be class of NP complete. So set is also NP complete.
Right.
And we can reduce independent set to set.
every problem in NP can be reduced to SAT, right?
Yeah. So independent set problem can be reduced to set. So independent set should belong to NP problems.
Right.
And you are saying that it also like independent set belongs to NP complete. So this is like here the contradiction comes.
Okay, okay. So let me try to explain. So let's take X as the independent set, okay, problem. Now we know X belongs to NP because this condition is satisfied.
Yes, sir.
Okay. Now we want to check for this condition, right? So we
Uh,
want to check.
so we are taking this example, right? The X equals to set and Y equals to IS.
No, we are taking X is equal to IS
Okay.
because that we want to check if X is an NP complete problem or not.
Okay.
Okay. So we want to check if IS is an NP complete problem or not. It is if it satisfies these two properties, right?
Okay. Yeah.
So we check the first property, yes, X belongs to NP, right?
Mhm.
Now we want to check this property for all Y. So we take all the NP problems, all Y in NP. So the question we want to ask is, does all NP problems Y reduce to the independent set, right?
Yes, sir.
This is the question we want to answer, right?
Yes, sir.
And if we answer this, we know that if this is yes, then we
Then
know
it
that
is
IS is
NP
yeah.
complete problem.
Okay, very good. So does Y reduce to S? So what Cook-Levin tells us that every problem in NP can be reduced to SAT.
Yes, sir.
So what it is telling, so this every problem is this Y only, right? So
Mm.
every problem in NP, every Y can be reduced. Y can be reduced
To set.
to SAT, right?
And set
And
can be
if
reduced to independent set.
yeah, and if so, what we actually have to check is whether SAT can be reduced to independent set.
It can be reduced because in the NP class problem, every problem can be reduced to set. So, like if we can reduce to set, we have to pre-process. And if we want to convert that again, so we have to post-process. So both ways convertible. So we can convert it to set to IS.
SAT to IS is possible, right?
Possible, yeah.
Yeah. So any problem, if you want to check if it is NP complete, just check if it belongs to NP and check if that problem, if SAT can be reduced to that problem.
So for every like in each case, we have to consider this set because we have to go by the theorem.
Yeah, but actually, the theorem. So now once you actually see, no, then it's necessarily every time you need not look at SAT. Some people look at another type of problem, NP complete problem, and they try to reduce that to, the problem which you want. So in general, if you can take any NP complete problem, which is known to be NP complete,
Password.
and reduce it to the problem X, whichever your X is, then X automatically becomes NP complete.
But sir, I got your point. But what I'm saying is, like here we are saying independent set is NP complete problem by proving this Y reduced to independent set.
Right.
What if we take X as set, like we take in the this below example,
Okay.
and Y is independent set? Then
Okay.
we can prove that independent set can be reduced to set problem. So in this case, the set will be NP complete and independent set problem will become NP only. So here the contradiction enters.
Okay. So if we take X as SAT, so X belongs to NP, and for all Y in NP, y reduces to x. So y reduces. So is this true? Does y reduce to sat always?
Yes, sir. This is like the theorem, Cook-Levin theorem.
Okay. For all y in NP, y reduces to sat. Okay. Okay. So
So what I'm saying is take y as independent set.
okay. So you're saying, okay. So y as independent. So independent set reduces to sat. Okay. All right.
So according to this statement, a NP complete problem can be reduced to NP complete problem. Is this true?
Yeah. So that's the thing. So if you will see that all NP complete problems can be reduced to one another. Yeah.
Okay, then this thing is true because independent set, and this like both are NP
Vertex.
complete problem,
Yeah.
and both can be reducible to each other.
Right.
And sir, can you give us like an example of an NP problem that is not NP complete?
Yeah. So uh, this one, no, factorization, no. Let me see.
Prime
Integer
factorization.
factorize. Yeah. So let me see if I integer. So if you see this, no algorithm has been published that can factor all integers in polynomial. That is, can fact can factor b bit number n in some constant case, some polynomial time. Okay. Neither the existence or non-existence of such algorithms has been proved, but it is generally suspected that they do not exist. Right. So this problem is clearly in class NP because you have an efficient checking algorithm. Okay. But it is generally suspected that it is not NP complete, though this has not been proven.
But sir,
Right.
we can prove that this is an NP complete problem by reducing it to set and then further reducing it to another problem.
Yeah. So that is the thing. We till now we don't know if we. So there isn't a efficient, or there is no way to. Till now, people have not come up with that reduction.
So everyone is like in living in confusion.
Yeah, because there is till now people have not come up with a way to reduce the uh, this integer factorization to SAT, or from SAT to integer factorization. If that is possible, then it is an NP complete problem.
Okay, sir. So this is the thing, like nothing is clear and everything is not clear. Oh, no.
Yeah.
Still, sir, I got clear.
Yeah,
Like more
and these
concepts are
concepts,
clear.
and these concepts are difficult, because it is not very clear, about whether uh, NP is equal to P, and whether an algorithm is actually NP complete or not, because you need a proof, right? And or you need a reduction. And till now, for many problems like this integer factorization, that reduction has not been shown, right? That's why it's not clear.
Okay, sir.
All right.
Thank you, sir, for your extra time.
Okay, no problem. Anyone else? Okay, Snail is asking, with respect to programming exam, will going through PPAs and GRPAs be enough? Yeah, I think so. I think it should be enough. Yeah, just keep your concepts clear for, you have gone through many algorithms, right? The main question or the main thing which you should do is when you read the problem, try to understand which type of algorithm it is, right? And is it dynamic programming, or should you use a greedy approach, or uh, can you translate the question to a graph, right? And then which algorithm you should apply. Those things, if you keep in mind, and of course, if you practice the algorithms well, I think it should be.
But
Shouldn't.
sir, I have one question regarding this. Like, will we be like asked by the question, like the questions whose algorithm will take time to write the code, like the Floyd virtual algorithm?
Uh, take time as in,
In writing the code.
see,
Like,
so
I'm just clearly asking, like, what kind of question will be there? Like, how much time will will that question will take to solve? In the
yeah, so there will be 4 to 5 questions, right? You all know the format, right? 4 to 5 uh, questions will be there, and uh, yeah, I think that's all I can say.
and so,
But
what will
see,
be the level of difficulty? Like, it will be like live coding questions or similar to GRPAs?
yeah, similar to GRPAs, yeah.
Okay, sir.
All right.
Thank you, sir.
Okay,
Thank you,
everyone.
sir. Good night,
Okay,
sir.
see you. Good night. Good night.
Good night, sir.